Hello, my name is Martin Martinez, and this is Lab 2 Lines of Charges. To introduce, similar to the last lab, this lab intends to identify how charged objects interact with neutral objects. We'll utilize two pieces of tape to measure their interactions and determine roughly the amount of excess charge present on both. Uh, During this first part of the experiment, we'll figure out which whether the piece of tape holds a negative or positive charge, similar to the last experiment. And after that, we're going to see how long or how much charge is needed to suspend a piece of tape. And then this time, instead of modeling them as point charges, we're rather going to treat them as a line of charges, and that's how we're going to find Q. At the end of the day, we're also analyzing how these results will affect Newton's second law and on the objects we use every day, such as these pieces of tape. Key principles we're going to be using are Coulomb's law, electric field and force, Newton's second law, and also the superposition principle. All the other laws we've used before. The superposition one is the only new one. That's just essentially saying that the net energy field is equal to the energy fields of each of the individuals. We're essentially just saying that the whole is the composition of its parts. Procedures could be pretty similar to the last one. Instead of assuming that the U-shaped tapes are point charges, we can assume that they're a line of point charges. We can also assume that those individual charges are distributed evenly about the line, and also that they are equal. We can also say that the charge equal at both ends of the tape, and then we can assume that both tapes have similar charges since they were kind of created the same way. So we'll charge the two pieces of U-tape and kind of put them together in order to calculate the forces. That's going to be the suspending one on top of the other. We'll place one of the pieces on top of the other, on top of another piece of tape in the lower tape, pull it away to kind of create that charge, and then we'll see what force is needed to repel the equal and opposite force of gravity down we'll find what force E of the electric field up needs to cancel the gravity down. This allows us to calculate the unknown charge Q. Similar to the last one, I had the similar expectations, especially now that I saw the last experiment, thinking that the charged shapes will repel since they have similar charges. I observed that they do. It was pretty similar to the last experiment. And the conclusion is that both have positive charge, and since they're both being modeled as charged, like line of charges, that all the charges in those on that line are the same. And it's kind of seen by the fact that negatives are attracted. And the next is the data calculation. So we had similar mass last time, used the same piece of tape. The distance between them was 0.010 meters. The length of the piece of tape, which is the difference, we actually had to consider the length of the piece of tape, was 0.19 meters. So we're going to take the force of gravity down from the top piece of the tape. We're able to find that it's negative 0.001862 newtons. We know that the force of electricity up has to equal that in order to be in equilibrium. So we say the force of the force of the electric field is 0.001862. And we assume that both the tapes have like charges, similar to the assumption we made last time. So we take this equation that we were able to find for the force of, or the actual electric field of a line of charges that we derived during lecture, and we're just essentially adding another Q to that. So that's how we find the force, and that's why we assume that the two charges are the same, and we're able to say KQ squared, which normally is KQ for just the electric field, but we add another Q in order to find the force. KQ squared divided by R square root of R squared plus L over 2 squared. The L over 2 squared the L is going to be the length of the tape. The R is going to be the distance between the two tapes. And that's the force is going to have to equal that 0.001862. So we actually solve that out. We come to have a Q of 4.3 times 10 to the negative 9th coulombs. The GlowScript code, we're able to create a couple methods to find the E field, just so we have to keep doing it over and over again. And also have a method that calculates the line charge and returns the line of charges. So we create we initialize the top and bottom line charges. and we create the F of electric field, just kind of initialize that, create a little scale factor so that the actual viewable is actually viewable, and then we're going to iterate through each DQ, every change in that little charge from the top. Um, then we'll actually, if you can see, we do it from the bottom as well. We do it at the same time, and that's how we find the full charge. And then we're just going to draw arrows to represent the force from each of those locations, and you can kind of see that in the output on the next slide. But with all that, we're able to say that we already knew the charge of the tape, but we're able to kind of model what's going on with the force of gravity and the electrical force canceling out the force of gravity. We can kind of see that here. So all those green arrows are going to come together to cancel out that, or essentially the white arrow upward is going to be the composition of all those green arrows, and then the arrow downward is going to be the force of gravity down. So what if we modeled the tapes as point charges like in the previous lab, compare the estimated values, and what you got. Um, so in this experiment, when I modeled it as a line charge, it was just a little bit smaller, but it ultimately should be about the same because ultimately it's going to be the same like force being created by the electrical field. But that was the only thing that really changed, and the what if would be the experiment last time. So it doesn't have to be that much of a hypothetical because we did. Um, but yeah, that's essentially, if we were to model it as a point charge, it'd be the exact same as the last experiment. I got a little bit smaller, but it should be about the same. And then how do these estimates differ? Why do you think it's closer? Because the line charges more accurately depict what the tape is actually going on. Because when we estimate it that it's just a point charge, we're not thinking, okay, that all the charges are distributed evenly, and also they're derived completely different ways. The point charge is just it's a completely different equation than the line charge. So that's why they differ there. But that's going to be the end of the lab, and thank you for watching.